Hey there, welcome to The Explainer. I am absolutely thrilled to have you here today because, well, we're going to be doing something pretty cool. We're unpacking the hidden geometry, the hidden structures of the everyday world right around us. We walk through our homes, we look at objects on our desks, we interact with things all day long without ever really seeing them for what they structurally are. Today, we're going to change that by looking at a fascinating breakdown of spatial geometry from our chapter that is literally hiding right in plain sight.
Okay, let's dive right into this. Think about it for a second. What do a musical drum and a birthday present actually have in common? On the surface, literally nothing, right? I mean, one makes a lot of noise, the other holds a surprise. But underneath those colorful exteriors, they share a profound connection in the realm of spatial awareness and physical dimensions. Believe it or not, they are governed by the exact same geometric laws.
So, moving right into section 1, everyday musical geometry. These are math shapes hiding in plain sight. Take a look at this. On one side, we've got this beautiful ringing golden bell. And right next to it, an abstract pink geometric cone. When you put them side by side like this, the illusion just totally falls away, doesn't it? The golden bell perfectly matches that abstract cone. The sloping sides, the circular base. The bell is simply a cone that's just been engineered to produce sound.
And we see this everywhere. Here's a harmonium. It's this complex, beautifully detailed musical instrument with keys and bellows and knobs. It honestly looks pretty intimidating to build. But then look at the simple, unadorned rectangular storage chest right next to it. Despite all of the harmonium's complexity, it shares the exact same three-dimensional structural boundaries as that simple box. Recognizing this, that's your first step in unlocking spatial intelligence. All right, section 2, anatomy of a gift box. We're going to peel back the layers here.
To do that, let's look at this fun little case study from our chapter. Here we've got Hina and Atif, and they are enthusiastically decorating a blue gift box for a friend's birthday. Now, it just looks like a cute, simple craft project. But if we pay really close attention to their dialogue, Hina and Atif are actually performing a highly functional breakdown of a rectangular prism. Let's listen to what they're saying.
Listen to what Hina says here. We will place 1 star on each face of the box. Now, by planning her decorations this way, she just unknowingly gave us our first absolutely crucial piece of architectural anatomy. She didn't just say, on the box. She specifically isolated the face. So, what exactly is a face in this context anyway? Well, a face is simply the flat surface of a 3D object. Literally every single flat panel you can touch on that rectangular gift box, the top, the bottom, the front, the back, and the sides, is a face. By placing 1 star on each, Hina is essentially doing the math. She's counting the exact number of flat surfaces that make up that specific 3D shape. But Atif, he takes it a step further. He says, we need 12 ribbons for each side or edge. Some will be short and some will be long. This is brilliant. There's actually some fascinating math hidden right there in his crafting needs. He doesn't just need a random handful of ribbons, he knows he specifically needs exactly 12 to completely outline the box. And that brings us right to our second definition. An edge is the line where 2 faces of a 3D shape meet. So the whole logic of Atif needing exactly 12 ribbons, it perfectly proves the geometry of a rectangular box. A box literally has 12 distinct lines where its flat panels intersect. Think about it. If he has 11 ribbons, a seam is left completely exposed. If he has 13, he's got one left over. The physical object absolutely demands exactly 12 edges. Which brings us to section 3, counting faces and edges. These are the universal rules of structure. Check this out. Here we have a tiny 6-sided die like you'd roll in a board game, and next to it, a massive yellow gift box being carried by 2 little mice. Obviously, this size difference is dramatic, but structurally, they are completely identical. The tiny die has 6 flat faces and 12 edges. The massive gift box has 6 flat faces and 12 edges. The structural rules of geometry remain completely absolute, regardless of how much you scale the object up or down. Now, to complete our architectural anatomy, we really need to look at what happens when those lines we just talked about literally crash into each other. A corner is the point where 3 or more edges meet. Think about the sharp, pointy bit of the dice or the box. This final anatomical term sets up the ultimate way we can categorize the entire physical world around us. All right, let's put this into practice with section 4, the corner challenge. It's time to become a spatial detective. So,
Let's try this sorting exercise straight from the chapter. We've got 3 distinct categories here: objects with no corners, objects with 1 corner, and objects with 3 corners. I want you to literally start mentally scanning the room you're sitting in right now. What objects around you would fit perfectly into these specific columns? Let's look at a few examples to get our gears turning. Take a simple, everyday orange, for example. Where does it go? Well, the orange is a sphere. It has this continuous, perfectly curved surface. There are absolutely no flat faces to intersect, which means there are 0 edges. And consequently, it belongs squarely in the no corners column. It is perfectly smooth geometry. Next up, we have a fun, colorful party hat. Now, remember that golden bell from earlier? Well, the party hat shares that exact same conical structure. It's got a circular, continuous base at the bottom, but the material travels upward to meet at a single, sharp point at the very top. This fun, everyday object is just a perfect visual anchor for the one-corner concept. Now, you might be wondering, why does all of this actually matter? Why are we spending time counting the ribbons on a gift box or the corners of a party hat? Well, because understanding edges, faces, and corners is the absolute bedrock foundation of architecture, design, and engineering. These simple, elementary exercises we explored today, this is exactly how we build complex spatial intelligence. Every skyscraper, every suspension bridge, every single piece of modern technology begins with understanding how 3D shapes interact in physical space. Before we wrap up, I want to leave you with this really provocative challenge from the project work section of the chapter. If you were handed a single flat sheet of cardboard, how would you manipulate it to build a 3D shape with only one face? Is that even possible? I highly encourage you to look around your environment today. What complex shapes are actually just simple geometry hiding in plain sight? Thank you so much for joining me for this explainer, and definitely keep exploring those hidden structures all around you.